Welcome to Talking Science, where we dive into science and space. Members of a research project a decade and a half in the making, Dr. Dick Manchester and Associate Professor Adam Deller are here to discuss the most strenuous testing of Einstein's general theory of relativity to date.
This is Trek Zone's Talkin' Science.
Well, don't forget Trek Zone membership available via the join button under each video on YouTube or via the trek.zone/support. Plus Trek Zone's on Twitter, Facebook, Instagram and your favourite podcast feed. Find us, like, follow and subscribe. Dr. Manchester, let's start with you first up. What exactly has just been announced?
What we've just announced is a long study of a system called the double pulsar, which nature gifted us with a while back. In fact, we discovered it at Parkes in New South Wales in 2003. And it's virtually an ideal system for investigating theories of gravity. And so we've been using it for that purpose and have been able to show that we just can't fault Einstein's theory of general relativity. It hangs in there.
He is a very smart man, as we were talking about off air, and that is a definite understatement. Well, this double pulsar, discovered by Moriang in 2003, as you say, was the ideal candidate to stress test Einstein's theory. What makes it so?
Well, there's a couple of important factors. One is that the pulsar that we've been observing spins quite rapidly. It spins 50 times every second, and so we get lots of data from it. And the other thing, and actually the more important thing, is that it's in orbit with another pulsar in a very, very tight orbit. These two stars go around each other every 2.5 hours, which is quite amazing. And it means that there are huge accelerations in this system. And so it's an ideal test bed for investigating theories of relativistic gravity.
Well, this double pulsar is incredible, as you say, one rotating 45 times every second, the other 2.8 times every second. With an orbit completed in about 2.5 hours, they are essentially cosmic lighthouses, Adam.
Yeah, that's right. So when a neutron star is born in a supernova explosion, the core of the massive star gets compressed down into a very, very small space. So it's only about 20 kilometers in diameter. And in doing so, it gains a very strong magnetic field and it starts to spin very fast. And the combination of those things leads to this production of a beam of radio emission coming out of the star, very intense. And so if that beam happens to sweep across us at the Earth, we see a blip of radio emission that we can pick up with the radio telescope. And because they're so massive, they're kind of like giant flywheels. Their rotation is very regular, and so we see these blips coming past in a very predictable way.
Well, the ticks or blips from the pulsars took around 2,400 years to reach us here on Earth, and through some maths and some clever thinking, you and the research team accurately predicted their arrival times. How am I there? Am I in the ballpark of the research?
Yeah, that's right. So basically, we start off with sort of like a simple model of the system. So we know that there's two stars and they're going around each other. We have a bit of information on the orbit, like its period and so on. And then gradually we make that model better every time we see that it's not quite good enough to predict the next round of clock ticks, or we predict the next round of clock ticks and they're not arriving quite when we think they should be. And so then we have to add some more information into the model, and we keep doing that until the model is describing the data that we have perfectly. And when you've got 20 billion of these clock ticks over 16 years, you can make a pretty detailed model, and you can include all of these tiny deviations from Newtonian gravity that are predicted by the general theory of relativity.
And Dick, over 16 years of studying this, Dr. Brad Tucker and I do Talking Science News every Tuesday, talking about long-term studies to get the data and then confirm the data. But 16 years, a very long time. How do things change in research methods, or do things change in research methods over that time, or do we have to sort of stick with what the establishment at the beginning there?
They certainly do change. I mean, you've been showing these nice pictures of the Parkes telescope, Marianne. That doesn't look the same now as it did in 2003 even, and certainly not the same as it did when it was constructed in 1961. So the instruments change. The techniques that we have available to us, supercomputers and such like, evolve, allow us to do more powerful analyses. And so, things do change a lot.
And how does Einstein's theory come into this? How have you and the team's research proven him right again?
Einstein's theory describes how gravity works, basically. So gravity is a key ingredient of what's driving or holding this system together. These two stars are whipping around each other, and so it's the theory of relativity is a fundamental way of describing what's going on here, and you just can't describe it with, say, Newtonian physics, as Adam was sort of alluding to before.
Well, a question to either of you. What's it like knowing Moryung or Parkes played the pivotal role in this decade and a half of research?
Well, for me, it's great. I've been there the whole time. In fact, I started work at Parkes more than 50 years ago. So that's quite a long time. So I have a very soft spot for Parkes.
Awesome.
So, it's been great.
It's a big international effort. It's a large team of people using telescopes spread across the globe. But it wouldn't have gotten started if we hadn't found this system, and it was found at Parkes, as Dick said, almost 20 years ago now. So, it's sort of like you feel like you've got pride of place in some way.
Well, with new radio telescopes coming online in the years ahead, like the Square Kilometre Array, what potential new discoveries are out there, Dick?
Well, there's lots of these systems out there. We only see a small fraction of them. There are several reasons for that. One is that some of them, with their lighthouse beams going around, that beam doesn't cross the Earth. So, if that beam doesn't swing across the Earth, we don't see any pulses. So there's probably about 2/3 or 3/4 of them that we can't see for that reason. Another reason is that many of them are very faint. And so the surveys that have been done up to now, or in fact all surveys really, even future ones, will be sensitivity limited. So things that are just too far away to detect, you don't detect. And so there's probably another factor of 5 or so involved in that. So potentially there are, if you had infinite sensitivity, you would detect hundreds of these things, even in our galaxy. But practically speaking, we could expect, say, in the next 10 years, maybe another 10 or dozen or so to be found. That may be optimistic.
Well, Adam, I've asked this question to a few of my guests in the past, but I always love to hear about working collaboratively with colleagues around the world. And this is such a long-term project. How has that collaboration been?
Yeah, it's been very different the last couple of years to previously, because, in pre-COVID times, we might catch up in person once every year or two or something like that. You'd run across people at a conference, you'd have the chance to sit down, huddle together in front of a laptop screen and look at something. And, those moments are usually the most exciting ones, when you get to see something new for the first time, because, they haven't published it, they haven't maybe shared it with the rest of the collaboration yet, but you happen to be there on the day that they've found it, and, that's when you get the buzz. The last couple of years, of course, we've all been kind of stuck at home on endless Zoom meetings, and progress is still made, but it doesn't quite have that same buzz, I've got to say. And it was then very great to get to the end of the road now, publish the results, and get to talk about it with a wider audience as well. Sort of brings back a little bit of that excitement again.
Having such a broadly distributed group of people all around the world involved in this, we often had meetings at rather uncomfortable times for some members of the team, but we persevered. Michael Kramer from in Bonn, was often up very late, and we were often up very early. But we managed it. It was fun.
And you also meet some interesting people as well, and different aspects of the same industry, same field for future collaborations as well. I guess networking is maybe one of the unsung things out of these international collaborations.
Everyone brings their own strengths to the collaboration, obviously. Like, so we don't have 16 experts on theory, there's someone that's really an expert on the theory, there's someone that's an expert on operating the telescope, someone that's an expert on doing the data processing. And then when you have your next idea of like, oh, actually, I'd really like to do this test with this other system or something, the person who is the expert to go and call and say, hey, I've got this idea. Do you think this will work? And they can say in 5 minutes, yeah, that's a great idea, let's pursue it. Or no, that's stupid because reason X. And, you make progress so much more quickly that way.
Dr. Dick Manchester and Professor Adam Deller, congratulations on being part of the team and finally having this research released. Thanks for beaming in to this edition of Talkin' Science.